Not is recording. Okay, so now it's a problem here because it's not a problem till now, because since this NMOS is not available, so whatever charge CL was having during a pre-charge phase, it should maintain that charge when clock again changes its state from 1 to 0. Okay, but it does not happen actually. The reason for this is the leakage currents. Okay, we know that there are leakage currents that flow through the transistor. Okay, and also there are diodes which are which are reverse biased, present within the device, within MOS. Okay, so this external diode represent that thing, that this reverse bias diodes are present inside this device. Okay, and also that this NMOS, when it is not conducting, even then there are some leakage currents that are flowing between drain and source. Okay, so what happens is that when clock is 1 and when the phase is of evaluation mode, even though this NMOS is not working, even though this NMOS is not uh, working. Okay, so what happens is that the charge which was there on CL, okay, this gets reduced, the charge gets reduced. Okay, the charge on CL reduced, okay, because of the leakage current that are flowing in this branch. When there is a small amount of leakage current, that will try to reduce the voltage of the load capacitance, and when the voltage reduces on the load capacitance, that will reduce the charge content of the load capacitance also. Okay, so who is the culprit here? The leakage currents are the culprit here, right? So now again, uh, again when it goes to 0 and when it goes to 0. Okay, again when it goes into pre-charge phase. Okay, and since in the evaluation phase this was not working, so we would expect that whatever charge was there on CL during the previous pre-charge phase, that same charge content should be present now also. But now but it doesn't happen like that. We will observe that it observes that there is a small reduction in the charge content of this load capacitance, and this reduction in charge content of load capacitance happens because of the leakage currents. So who is the culprit here? The culprit is uh, the culprit are the leakage currents. Okay, and since the value of these leakage currents are small, the magnitude of leakage currents are small, so it will result in a small small reduction in the charge content of the load capacitance, and we don't want that. We don't want this thing to happen, because in some cases it may be significant enough. Okay, so the cases where the threshold voltage of the devices are low, in those cases it can be very critical. Okay, so this is one problem that is uh, there, called as charge leakage. Okay, and look at this. Look at this. Here, when clock is 0, okay, this is the pre-charge phase. This is the pre-charge phase. In pre-charge, what happens? The output voltage, this output voltage, okay, which is the voltage across CL, output voltage rises because it is connected to VDD directly, because this is on. Okay, and it goes to its maximum value. Okay, now when the clock changes from 0 to 1, and this is the evaluation phase, and when clock goes to 1, okay, uh, and when a is 0, okay, this path is not available, we expect that whatever charge content, whatever maximum charge was there during the previous precharge phase, it should maintain that level. This level should be maintained like this, okay, like this. But it doesn't happen because of these leakage currents. The charge content of the load capacitance and hence the output voltage reduces, and it goes by some slope in the downward direction, and you will find that at the end of this cycle there is a reduction in the output voltage by this amount. Okay, we wanted this level, but the level has got reduced to this. So this is the difference that occurs because of this effect. Okay. And this we call this as a charge leakage issue in dynamic design, in dynamic logic circuits. Okay. So this is what is written here. The operation of a dynamic gate relies on the dynamic storage of the output value on a capacitor. Okay, and if the pull down network is off, the output should ideally remain at the pre-charged state of VDD during the evaluation phase. Okay, however, this charge gradually leaks away due to leakage currents, eventually resulting in a malfunctioning of the gate. Okay, this is one issue in these dynamic circuits. Okay, and so what is the solution for this charge leakage problem? The solution, because it is happening like that, the charge is getting leaked away during every evaluation phase of the clock cycle, clock half cycle. Okay, so it becomes a necessity here to have a minimal clock rate. Okay, which is typically of the order of a few kilohertz. Okay, so it should be just fast enough so that it maintains or it recharges the charge content of the load capacitance before it gets discharged. Okay, so it should have at least that speed of the clock signal which is being applied at the input of these dynamic gates. Okay, now so it becomes a necessity that you cannot operate it with a very low rate clock signal. Okay, so this becomes a kind of limitation. Now there's one more solution to this. This can be counteracted by reducing the output impedance on the output node during evaluation. Look at this circuit. Look at this circuit. Okay. So what is added here is so we have this PMOS. Okay, this PMOS as it was present here, there in the dynamic circuit. This NMOS, right? And here this is the uh, pull down network. Okay, so this is the pull down network that consists of two series combination of two NMOS transistors. Okay, so can anyone tell me what logic function will it implement? Yeah. Okay, this which logic function does this dynamic circuit is implementing? Output. If someone asks you that what is the equation for output here, can you tell me? Anyone? Which gate it is implementing? OR gate, AND gate, NAND gate?
And get
Okay, someone said AND gate, right? But can you tell me why it is AND gate? Why it is AND gate?
Sir, A, B, and clock are in series.
Okay, A, B are in series, and we know that whenever A, B are in series, the series employs the AND connection, right? Right. Okay, fine. That's okay. And whenever the devices are in parallel, that employs an OR connection. Okay. So this will employ an AND gate. This is right. But we know that these CMOS circuits are inherently inverting in nature. Okay. So this will, being more specific, this will be actually not of AND. Okay. So here output you will get the function that will be equal to A dot B bar. Okay. So keep this in mind that these CMOS gates are inherently inverting in nature. Okay. Now, so uh, okay, okay. So we were here like this is NMOS, this is PMOS, this is the pull down network. Okay, and this is the output terminal, and okay, so there was a problem here that when during the evaluation phase, when clock was one and clock was one here, so this is available, this is not available. Okay, and whatever charge content of this load capacitance was, that might get leaked away, even though when the folder network is off, even though they are not working, there is a chance that the charge content of this CL may get leaked away because of the leakage current that are present, that are flowing through these devices. Okay, now this is the problem. So what can be solution? So in this current scenario, if we can provide a connection between this output node and VD somehow, then in this case the level of output will be maintained. Okay, so look at this. This is a PMOS. Okay, this is a PMOS, and the ground is connected to, sorry, and the gate is connected to ground, which is actually logic 0. So it means that this PMOS is always on. This PMOS is always on, right? So this PMOS is always conducting. So this output is actually connected to VDD directly here in this by this through this branch, through this PMOS, and that will maintain the value of output node here. So even though because of these leakage currents, the value of this load capacitance will not decrease. Okay, so this can be one solution, that insert one PMOS, one weak PMOS, not a strong one. One weak PMOS means a small sized PMOS. Okay, here between output terminal and VDD, and this is always on. So when during evaluation phase, this will make sure that the value of CL, the output voltage is maintained to high, the charge content of CL is maintained because of this branch, which is always available to this output node. Okay, so this can be one solution, right? And this particular PMOS is called as a bleeder transistor because it is always in kind of on. It is always bleeding. It is always conducting. So it's called as a bleeder transistor connected to eliminate this charge leakage problem in dynamic circuits. Okay. Okay, now, so the issue here is, okay, this can be a solution, but the problem is that this PMOS is always on. This PMOS is always on. And when this PMOS is always on, it will dissipate power always, all the time it will be dissipating power. And that can be another issue. Okay, so what can be done to solve this issue? So that we want this PMOS to be on only under certain conditions. Okay, so look at this one, the same circuit. This is the कुछ है क्या भाई? और वो ठीक चल रहा है? हैप्पी न्यू ईयर। ये जो मिला था ना, इसी को यूज कर रहे हैं, इसी से लिखते हैं इसमें। Okay, so this is the same bleeder transistor. Okay, and there is one small modification here, that there is one inverter, okay, that is present between the output and the gate of this bleeder transistor. Okay, so what happens is that when output is low, when output becomes 0, only then it will become high. Okay, and this will turn off. Okay, right? And uh, only when output becomes high here, okay, output becomes high, you will have a 0 here, and that will make this breeder transistor on. Okay, so it will conduct only when the output is high. Okay, only when there is a charge content on the load capacitance. Okay, and there is a need to maintain that charge uh, on the load capacitance. Okay, it will not conduct, because it will not conduct when output is low. Okay, so this problem resolved like this. Okay, so look at here, try to uh, get it out. There is an issue here. Okay, so these are some solutions to the charge leakage problem in dynamic circuit. Okay, now there is one more issue called as known as charge sharing. Charge sharing. Okay, so let us see what is charge sharing problem in dynamic circuit. Okay, now look at this example. Okay, look at this example. So what is this charge sharing problem actually is? Uh, the charge stored originally on the load capacitance CL, okay, is redistributed or shared over CL and CA. Okay, CA is this capacitance, leading to reduced robustness. Okay, so look at this diagram. And this is the load capacitance that is present. Okay, and this is the PMOS, this is NMOS, right? And this B is 0, the input is 0. It means that this NMOS is not working, so this path is not available. This path is open circuit. Okay, okay, and this A is changing. The input A is, let's say, 1. Okay, input A is 1, so it means that this NMOS is conducting. Okay, and if we assume that this PMOS is not conducting, that is clock is 1, so this NMOS is available, right? Now, we know that there are parasitic capacitances associated with every device. Okay, so this is the parasitic capacitance associated with device NMOS A. Okay, and this is the parasitic capacitance associated with the NMOS B. And since this device B, NMOS B is not conducting, so we will not bother about this CB. Okay, we only bother about this CA in this condition because this NMOS is on, NMOS A is on. So what happens is this path is available, okay, between this node and this node. Okay, and look, can we form a closed loop path here? So start from ground, okay, and come here like this, and it will go to the ground. Okay, again this is ground, this is ground, so they are same. So like this, the current will flow like this in the closed path. Okay, like this. And because of this closed loop path that forms, the charge content of Cl gets distributed, gets shared with Cl. And if there is a sharing, because of this sharing, the charge content of Cl gets reduced. The charge content gets reduced because of this sharing. Okay, and the charge content of Ca will increase. Okay, so overall result is that the load capacitance charge content gets reduced because of this charge sharing, and this is again a problem. We do not want this charge content to get reduced under this situation. Okay, this should reduce to zero only when this path is available completely. Okay, but under this condition, a can be 1, b can be 0, it is possible. So this path is not available because this is off. If this is off, this path is not available, it means that this output node should be maintained at logic 1, logic high. Okay, so it should have full charge, which was available to it during pre-charge phase. Okay, but because of this situation, the charge content of Cl is getting reduced and it's getting shared with Ca. Okay, and this might pose a problem in future. Okay, so this is again one more issue here in dynamic circuits. Okay. So there could be some solutions to this, right? Okay. There's one more issue here in dynamic gates, and this occurs when we cascade uh, many dynamic gates. At least two dynamic gates are cascaded, means they are connected back to back. So the output of one is feeding to the input of other. So let's see. This is the first phase. Okay. This is the first phase. The output of this dynamic gate is serving as the input to this dynamic gate. Okay. And look at this. The two clock signals. Okay. PMOS, NMOS, PMOS, and NMOS. So under this scenario, if we try to understand this issue, what happens during the cascading issue when we cascade two or more dynamic gates back to back, what will happen? This is clock. Okay, this is 0, this is 1, right? During 0, this is pre-charge phase, and this is evaluation time. Okay, during pre-charge, the output 1 should be high. Output 1 would be connected to VDD. So this is high, right? Output 2 will also be connected to VDD because the same clock is feeding to these two dynamic gates. Okay, so output 2 is also high. Look at here during field charge. Okay, now when clock enters into evaluation mode, when clock changes from 0 to 1 and we enter into evaluation mode, and let's say that in evaluation mode, the input signal, that is this one, goes to 1. Earlier it was 0, now it has changed to 1. Okay, now this output was high. Okay, this input has become 1, and this is evaluation, so this is available, this is available, this is not available, this is not available. Okay, so what is the scene here? What is the scene here? So this is 1, so this is available, right? Now this is available, so we expect that output 1 should uh, go to logic 0, and it will discharge its charge content present on the load capacitance via this path to ground, and it should become a logic 1 to logic 0, right? Okay, this thing will happen, this thing will happen. Okay, and when output 1 changes from 1 to 0, so it means that finally a 0 is present at the input of next gate, and this 0 will make this NMOS off. So ultimately this path is not available, and the output 2 value should be maintained at logic high, right? This should be the normal operation of these two dynamic gates which are connected back to back. But what is the issue here? What is the problem here? The problem comes here because we know that uh, this output 1, when it is changing its state from 1 to 0, it takes some time. Look at this slope. The transition from logic 1 to 0 will take some time. Okay, it is taking some time. This time propagation delay when output changes from high to low. So this is actually T P H L for first stage. Okay, okay, this is one thing. We will not go into this now. The point here is since this takes some time to change from 1 to 0, so for a certain duration of time it was actually at higher level, and if this is the threshold voltage level, okay, if this is the minimum level, okay, and if this is the threshold voltage mark, okay, so for this much duration of time it was actually above threshold level of NMOS, and it means that uh, for this duration of time the input was not 0, input was actually 1. Okay, and when for this small duration of time when input was actually 1, for that duration of time this NMOS would be available. Okay, this NMOS would be available. And for that duration of time this path is available. So what will have this on the what impact does this have on the value of output 2? That for in that small duration the output 2 would try to discharge from high to low. Okay, and this is what happens. Look at this, output 2 needs to be 1. We wanted this level for output 2, but due to this effect it is reducing some charge in that small time window, although it will not lose all of its charge value, but because this time window is small, but whatever, it will lose some of its charge content, and it will come from this level to this level. So finally you will get this level at output 2, which is which is below which is below logic 1 level by this value. Okay, now it may lead to some incorrect output value at output 2, right? And if we have multiple stages connected back to back, if we have 3, 4, 5, 6, many number of stages connected in cascaded style, then it may lead to some more even critical problems. Okay, so this is also one issue here, and there are solutions to this also. There are solutions to this also. And the solution will come in terms of the modification in the circuit. Okay, so some other logic style was proposed by Krambeck in 1982 to combat to overcome the problems that were faced in dynamic logic. Okay, and that next logic was called as domino logic. So domino logic tries to overcome the losses or the demerits that we face in dynamic logic. So basically, domino logic will be this is the same PDN network. Okay, this is the same PMOS. This is the same NMOS. So in between PMOS and NMOS, we have the PN network, and output is taken from here, right? And only what small change is done here is that they have inserted one inverter here, one inverter between two stage, between first and second stage, or between every stage. Okay, so output of stage 1 is being fed to the input of stage 2 via an inverter, via an inverter. Okay, and just for a quick review, that what would have this impact on here. Look at this. If we had an inverter here connected, okay, the output was 1, output was 1, okay, output was 1 here, and it is okay, it is changing from 1 to 0. Okay, and this is the threshold level, this is the least level. So during this time, this NMOS will take this part as actually logic high, okay, logic 1, because the value is still above its threshold value. So by inserting an inverter here, okay, for this duration of time, okay, this 1 will actually be served as 0 to this NMOS, and this will remain off. And if this is off, the output 2 charge will not decrease, and it will be maintained at this level. Okay, and when it goes here below VT and below the threshold voltage mark for NMOS transistor, this becomes this can be treated as a 0, here. Okay, so when output becomes 1 to 0, so this will become 0 to 1, 0 to 1. Okay, 0 to 1, and whatever logic was there, that would be available here. Okay, and if it is 1, so this will become finally conducting. So this path would be available, and output 2 will go to 0. So you will find that this output 2 uh, goes to 0 like this. If we are using domino logic, but there's one more point, that after each stage we are using an inverter. Okay, so output 2 will also be fed to an inverter, and this would be the final output. Okay, so output 2 becomes 0, and invert of 0 becomes 1. So final output, when we plot this, the final output would be 1. Okay, so you will get the output in inverted form. Okay, because this inverter has been introduced as a new element here, so the outputs are available, but they are available in actually we can say that this is available in non-inverted form, because earlier it was available in inverted form. Remember, this was when we have two transistors, this was not actually AND, this was implementation of NAND. Okay, now when we insert inverter here, it becomes here AND. So all the outputs are available, but in non-inverted form in domino logic. Okay, so this is what happens when we insert when we insert inverters here in the circuit. So it tries to overcome some of the issues that were there in the dynamic gates. Okay. So this inverter is the only change that was done in the cascading of dynamic gates, and it is called as a domino logic, a new kind of logic. Okay. So this is the same illustration that we had just seen. Okay, in the graph, and these are the main points. So if one assumes that all the inputs of a domino gate are outputs of other domino gates, then it is ensured that all inputs are set to 0 at the end of the pre-charge phase, and that only transitions during evaluation are 0 to 1 transition. Okay. And this is the theory part. Again, this is trying to explain the thing that we had just seen in the form of operation of domino logic. Okay. I will not go in the theory part. You have understood it, or you can also, because all these portions, this dynamic domino basically, and basically this topic of combinational logic design, all these topics I would be taking from the book Rabe, Rabaey. Okay. This combinational logic design and sequential logic design, both combinational and sequential logic design. Both of these topics would be taken from the same books. I will be referring to Rabi. Okay. So just there's one reading assignment, one reading homework. Read this topic, NP CMOS topic from Rabi. That is there on page number 288. Okay. And also read this. There is a small section, 6.4, uh, at page number 289. This talks about how to choose, proper logic gate for implementation, for the design. Okay. And this NPCMOS is also called as NORA logic. NORA stands for race, no race, NORA logic. Okay. So tell me anything, any point, any doubts till here? Then we can go into sequential circuits. We can go for sequential circuits. Yeah, students, any issue, any doubts till now from the combinational circuits that we have seen? Yes, Abhishek Singh. Abhishek Singh, are you
Yes,
listening?
sir. Hello?
Abhishek, any doubts here?
No, sir.
No? Devadatta Jena, Devadatta
Yes,
Jena.
sir. Yes, yes, sir.
Yeah. Are you following the lectures?
Yes, sir.
Hmm? Okay. Rajeshri Malik. Rajeshri Malik. Rajeshri Malik. Are you listening? Rajeshri Malik. Hmm? Hello. It looks like that Rajashri Malik is not following. Okay, so let's go to the next topic. The topic for sequential circuits. Till now we had seen combinational circuits, and there is a difference. We know the difference between sequential and combinational circuits. Basically, the basic difference is of memory. Okay, so sequential circuits are something that contain memory part also. And what is memory? If you try to define it by looking at yourself, let's look at ourselves. We have memory. Okay, humans have memory. So if we have memory, that it means that we can recall the previous data, the previous information, the previous events, and then we can take the current decision. Okay. So if we have some experience, some bad, if we have some bad experience related to one particular event, and if in future we go to the same event, we face the same event, then we will try to memorize, we will try to figure it out that what happened during the previous encounter, and based on that experience we will decide on that particular day that okay, we should take that decision. So this is the usefulness of memory, that when we have memory, or when a circuit is having memory, the current in output the current output value will be decided on the current inputs values as well as the previous input and output values. Okay. And but this facility was not available in combinational logic circuits. So combinational logic circuits described earlier have the property that the output of a logic block is only a function of the current input values. Whatever is the current input value, that will decide the current output value. It doesn't have memory, so it cannot go into the previous experiences and take out some wisdom from there and then decide about the current output value. It does not have that facility. It just calculates. It just performs some logical operations based on the current input values. Okay. But we know that to make a useful system, we should have memory part in that, and hence virtually all the practical and useful things require storage of state storage of state information, leading to another class of circuits called as sequential logic circuits. Okay. So in these circuits, what happens that the output not only depends on the current values of the input, okay, but also upon the preceding or the previous input values. Okay. Look at this diagram. This is the general diagram of a finite state machine, which is an example of a sequential circuit. Okay. So we have this combination logic. This is the combination logic, which will just perform the logical operation. This will just perform the logical operation. Okay. And this is the memory part, registers. Basically, this is a D-type flip-flop here, present here. So we have a combination logic, combo logic. We call this also as combo logic, or that will perform the logical operation. And we have a memory part here. Okay. Inputs are fed to the combination logic. The output is taken from the combination logic. Okay. And also the state information is fed to the memory part, and the output of this memory is fed as current state information to the combination logic input. So we can say that the output of the sequential circuit or finite state machine here depends on the current input values as well as the current state value. And current state value in turn is dependent on the next state, which is again depending on the inputs, current input and current state. Okay. So this is a general diagram of a finite state machine. So basically the thing is that we have a memory in addition to the combination logic to form a sequential circuit. Okay. And the memory would be operated with the help of a clock signal here. Okay. And this small triangle means this is edge triggered. This is edge triggered. Okay. We can have level triggered and edge triggered type of memory. Okay, level triggered memory are called latches, and edge triggered memory are called, what are the examples? The examples are flip flops. Okay. Okay. So now let us see how to. There are some timing definitions which are important from sequential circuits point of view. So the first important definition is setup time. Okay. TSU, setup time. So what is this? This is the time that the data input, the inputs. So remember, there was a combination logic, combo logic, and there was a D flip flop here. D flip flop, just we had seen. This is the input, and this is connected like this, and this is output. Okay, just keep this thing in mind. Keep this diagram in mind. So setup time is the time that the data input or D inputs, means it is referring to this D flip flop. Okay, D inputs must be valid before the clock transition. Okay, so we know that the clock changes. The clock changes like this. Okay, and this is a transition from 0 to 1. This is a transition from 1 to 0, and then back to 1, back to 0. And the flip-flops operate only at the transitions. Okay, transitions. Okay, so setup time is defined uh, as the time that the data inputs or the day inputs, means this day inputs, must be valid before the clock transition. So if we draw for D input, it means that whatever data we wish to feed into this D flip flop at this transition of clock signal, it should be available. Uh, it should be available just before this clock transition occurs. It means that it should be available in advance by a small amount of time, and that time is called setup time. Okay, so I can, for example, if I say that, okay, that students, your class timing is 3:30 p.m. Okay, but there is a condition: all the students should be present at 3:25 p.m. Okay, although the class will start at 3:30 p.m., but I want all the students to be present 5 minutes beforehand. Okay, so that 5 minutes that I am taking as a condition, putting as a condition, so that I want every student to be present 5 minutes before the start of the time of the class. So that can be referred to as a setup time. Just to relate that thing. Similarly, there is a concept called as hold time, T hold. This is the time that the data input must remain valid after the clock edge. So when the clock edge uh, passes, okay, so it's like when the class ends. Suppose the class ending time is 5 p.m. Okay, but I want the students should leave the hall, should leave the class only at 5 p.m. 5 p.m. and 5 minutes. Okay, so the class timing is, let's say, 1700 hours. But if I put a condition that students cannot leave at 1700 hours, they should wait for an extra 5 time, and they would be able to leave only at 1705 hours. So this extra 5 time that I am inserting here after the ending of the event, this can be referred to as hold time here. So it is a condition put on the signal so that it remains intact there, it remains held there for a small duration of time, even after the clock has passed, the edge has passed. Okay. Uh, so some duration before and some duration after this transition. So this first is the setup time, T setup, and the second is hold time, t hold. Okay. If setup and hold times are met, the data at the day input is copied to the queue output after a worst case propagation delay with reference to the clock edge denoted by TCQ. Remember, look at here. This is the D flip flop. Okay, and if setup and hold times are met, then this D input would be transferred to the output Q of this D flip flop. Okay, this is the clock signal. This is the clock. Okay, and this transfer will take place after worst case propagation delay. Okay, and this worst case propagation delay will take into account the setup time, hold time, and some other times into it. Okay, and this is denoted by TCQ. TCQ, and this is, since this is the worst case propagation delay, so it will involve all the timing delays that are there by definition, that are there for the circuit, and it will have the maximum value because this is the worst case delay. Okay, so uh, let's say this TP logic is the worst case propagation delay for logic. Now we have a logical function here. Remember, this is the logical function and this is the memory part. Okay. If for logical function we have a definition, a term TP logic, which is known as worst case propagation delay for the logical part, not for the memory part. This is logical part. Okay, then the time period for the clock signal. Okay. This is the time period of clock signal. So time period means okay. So there was net issue here. So basically, these two conditions should be met These two are the critical conditions. This one, these two equations. Okay, which should be met for any sequential circuit which is to be designed properly and which is to be expected to work properly. Okay. And generally, the TP logic is small, and TCQ and setup time are more critical for the design part. Okay. This is the general behavior. And look at this diagram, this timing diagram, this waveform. This x-axis is the time axis, and we have here the clock signal. Okay. The D means the input to that memory part, and Q is the output of memory part. So if this is a memory D flip flop, and remember that again there was a combo logic, combinational block, combo block, and there was a D flip flop block. This was input, this was output, and this was fed here, and this was coming here. Okay. This was clock signal. Clock signal. Okay. So according to the definitions that we had just seen, so this is an edge triggered flip flop. Okay. This is a let's say this is a positive edge triggered D flip flop. That means that all the events will be captured during the positive transition. So whenever the clock signal makes a transition from 0 to 1, okay, during this transition, the events will be captured. Okay, and let us take the middle portion here, which is coming here, and all the things will be calculated with reference to this point. Okay, for each, uh, for each of these, rising edge. If this is a positive edge triggered flip flop, so all these rising edges are important for a positive edge triggered flip flop. Okay, and for a negative edge triggered flip flop, these falling edges are important. Okay, but since we have assumed that this is a positive edge triggered flip flop, so all the things will be calculated with reference to this transition, which is occurring between 0 to 1 for the clock signal. Okay. So the data, this is the data, and by definition, the data should be stable, should be available in advance to this clock transition by a certain duration of time, which is called as the setup time. Okay, and it should also remain valid for a certain duration of time even after the clock transition has occurred, called as the hold time. This is called as the hold time. Okay, and for this Q, there was a definition for TCQ. Okay, TCQ, and look at here. TCQ was the worst case propagation delay, after which the data from input is transferred to output Q. Okay, so this is the output Q output. Okay, and since this is a D flip flop, so basically the D input is getting transferred to the Q output, same, without any changes, after a certain duration of time, certain propagation delay, called as the TCQ, or this is the worst case propagation delay. Okay, and after this TCQ, this whole of data, this data comes here at Q, at output. Okay, So this is how these definitions are here, are here, and just to go quick on these topics which are familiar for us. So there are some static and dynamic memory part. Okay. Static and dynamic memory. So what are static memories? Are the memories that are that preserve the state as long as the power is turned on. Okay, and the concept behind these static memories is they are built using positive feedback concept, also called as regeneration. Okay, and they are most useful when the register need not be updated for extended periods of time. Okay, so in these conditions, static memories are most useful to build. And such example of static memory is when configuration data is loaded at power up time during in the microprocessor. Okay. Then memory based on positive feedback fall under the class of elements we know that as multi-vibrator circuits. So all these come under that category, multi-vibrator. And we know that there are three types of multi-vibrator: astable, monostable, and bistable. Okay. And out of these, the bistable element, the bistable multi-vibrator, is the most popular representative. Okay. But other elements such as monostable and astable circuits are also used frequently for other applications. Okay. As long as the memory part is there, this is the most popular multi-vibrator which would be used here. Okay. Okay. Go up. Okay, right. Now, the dynamic memories are those memories which store data for a short period of time, on the order of milliseconds. Okay. They cannot hold data for a long duration of time because they are based on the charge content of the parasitic capacitors. And we had just seen that parasitic capacitors tends to lose charge with time because of the leakage currents that are flowing in the circuit. Okay, so they are based on the principle of temporary charge storage on parasitic capacitors. Okay, associated with the MOS devices. And as with dynamic logic discussed earlier, the capacitors have to be refreshed periodically to annihilate charge leakage. We had seen this thing. Okay. And but there is one thing that dynamic memories are simpler and resulting in significantly higher performance and lower power dissipation. Okay, because they are just one MOSFET and one capacitor, nothing else. And so they are simpler to design, they occupy less space, and their performance is also high. And they are most useful in data path circuits that require high performance levels. And but one thing is that it should be periodically clocked, otherwise it can lose its charge content. Okay, so it should be periodically refreshed. Okay. Now, let us see this also: latches versus registers. You are again aware of these things from your digital electronic circuit subject. The most important difference between latches and registers are that latches are level triggered, level sensitive, whereas registers are edge triggered or edge sensitive. Okay, so latch and both of these are memory. Both of these are memory basically. Latch is an essential component of edge triggered register. Okay, so we make We construct an edge triggered register using latch. Okay. Basically, latch is a level sensitive circuit, and we can have a positive level and negative level latch. Okay, just like we have positive and negative edge triggered flip flops, and it operates in two modes. One is transparent mode, and the other one is hold mode. So let us look at, suppose this is a positive latch, positive latch. This is the input, this is output. Okay, this is clock. So this is latch, D latch, which is positive. Positive means it will, when clock is 1, this is a transparent mode, trans, and this is when clock is 0, this is hold mode. And clock is 1, again, this is transparent mode. Okay, and it will continue like this. So when it is in transparent mode, okay, when clock is 1, clock is high. When clock is high, it is in transparent mode. Okay, and what happens? The input value is transferred to output. When input value, whatever input value we are having, that will get transferred to output. So look at this part getting transferred here, transferred. Okay, and when it is in hold mode, that is when clock signal is 0. When clock signal is 0. What happens here? When it is in hold mode, it should hold the uh, it should hold the last content that it held during transparent mode. Okay, and this is the edge. This is when this clock 1. Okay, and when last point was this one, this kind. Okay, that came here, and it will keep on maintaining that last content like this. Okay, and when it again enters into transparent mode, then it starts copying the content from the input. So this part will copied here, copied here, copied here, copied like this. Okay, so remember, look at here. When it was in hold mode for this duration of time, this input was irrelevant to the latch. It did not affect the output value. The last content was played during hold. The last content was held tightly. It was not lost, and it started changing only when it entered into transparent mode. Okay, so transparent mode, it copies data from input to output. Hold mode, it hold the last copied data into it. Again in transparent, it starts to copy the current data. Again into, when it goes into hold mode, it hold tight the last copied data into it. So this is how the latch works, positive latch. Okay, and this is a negative latch. So when clock is 0, this becomes the transparent mode, and when clock is 1, this becomes the hold mode. That is the only difference, and all the operation will remain same. Okay, so this setup and hold time requirements to be filled around falling edge of the clock for a positive latch. Okay, so what happens here, because the falling edge, this one, when it is falling from 1 to 0. Okay, so this is where it is entering from transparent to hold. So till now it was copying the data, and after this it has to hold that data. Okay, so this edge is important here. So setup and hold time requirements should be met at around this falling edge for a positive latch. Okay. Okay. So basically, latch is a level sensitive circuit, okay, which works in two modes, transparent and hold mode. Okay. We can have a positive level latch, we can have a negative level latch, right? Now, so registers are as triggered. Registers are as triggered. Okay. So they capture the data only at rising edge or at falling edge. So we can have a positive or uh, negative edge triggered, right? And they are built using latches. The latches are built. Latches are used for building the registers. And most of the time, you will see this master-slave register in action, the most popular register. Okay. We can also have other types of registers like glitch registers and others. So this one diagram is showing the uh, difference between the latch operation and the register operation. So latch stores data when clock is low, let's say, and it stores data when clock rises. So this is a rising edge, positive edge register, and this is storing data when clock is low. So this is a negative level latch. So look at here, when clock is 0, 1, 0, 1, 0, 1, when clock is low, when clock is 0, when clock is 0, clock is 0 here, the output uh, stores data, right? So it holds data when clock is low. So basically, this is a positive latch. In positive, it is copying data, and when it enters into negative, it stores that data. Okay. So when it is in one transparent mode, it copies the data, right? So till here, this output will be same as input. Okay, this will be same, and when it enters into 0, the last copied data is held for this duration of time. This will maintain the last copied data, and when again it goes into transparent mode 1, it starts copying, it starts following the input. So whatever input changes takes place, that change will be reflected here like this. Okay, and when it enters into hold mode, the last copied data, that is this last copied data, will be maintained throughout this hold mode like this, and it will continue like this. Okay, now look at here, this is a D type register which uh, uh, which is an edge triggered flip flop. So let us just see. So when clock is 0, 1, 0, 1, 0, 1, this is rising edge. When clock is rising, so this is a D. Okay, the same data is applied here to this latch and flip flop, and latch output is like this. Let us see what is the output of flip flop. Okay, so it captures data at rising edge. So when clock is rising from 0 to 1, at this instant of time, whatever is the value of D will be captured here, and this value is maintained for the rest of the cycle. So till here it will be maintained like this. Again, this is rising edge. The value of D is this one. So this will be set here, captured here, and this level will be maintained for the next, next duration of time like this. Again, this is rising edge. Okay, and at this edge the value of D is 0, so this captures 0 here, and this 0 level will be maintained for the next time cycle of the clock. Okay, so this is how. And look at the output of latch is completely different from the output of flip flop. Okay, so beware, be careful when you are designing digital circuits, because if you use latch instead of registers and vice versa, then the output may go wrong completely. Okay, so you should be clear that when you want to use a register and when you want to use a latch. But basically, generally, we avoid using latches. We prefer using flip-flops in the digital circuits. Okay. Okay, then we will start this next topic in the next class. So what you can do here is you can give your attendance in the chat box. You write your name and write your roll number and name in the chat box. And if anyone is having any doubt, he or she can ask.